last topic of this course for this year, and it's a look at displays. The displays are actually important in their own, because the display is the most expensive component of the bill of material of a smartphone. So again, consider that the smartphone is the biggest business in the among electronic systems, and considering the bill of material, especially for large phones, the display is about 20% of the total cost for the considering phone components and phone fabrication. Of course, you're not considering the let's say the development costs of hardware and software, but just the bill of material. This is, for example, the iPhone 6 Plus, which is a relatively large phone, and you see it's a little bit more than 20%. The other most important cost is the processor, which is this one. So depending on how big is the screen, the display can cost more than the processor. This is BOMI, stands for bill of material. You see, here it's included everything. This is the assembly. Right? The assembly is a very small part of everything. The rest is just, let's say, the cost of different components. Okay, now we probably need to say something about light. Probably you already know some of the concepts, but I'm not sure about that, so it's useful to remember. To remind, the most important things. So this is the spectrum of visible light from red to blue. Below red, at frequencies below red, we have the infrared region. And above the blue, at frequencies higher than the blue, we have the ultraviolet region. Ultraviolet rays. In between, of course, we had the visible light. So when we talk about visible light, very often, instead of speaking about frequencies, we speak about wavelength. And then we have the red, which has a wavelength of 780 nanometers, and let's say the blue, which has a wavelength of 380 nanometers. We indicate the wavelength with the letter lambda, and of course the wavelength is inversely proportional to the frequency. The relationship is this one: the frequency is equal to c over the wavelength. This c is the speed of light, the propagation velocity of the electromagnetic wave in general, and of course also of visible light in vacuum. So this is the speed of light, and it's a number which is useful to keep in mind, is 3 times 10 to the power of 8 meters per second. Okay, this is the wavelength. TH. Okay, the second thing to remember is that, of course, when we speak of light, we can discuss it as a wave, or we can discuss it as particles, because there is always this wave-particle duality. So, of course, when we talk about wave, it's useful to talk about frequency and wavelength. If we think of light in terms of particle, we must remember that light is transmitted by a bunch of particles, which are called photons, which have an energy that is proportional to their frequency. So the energy of a photon So the photons are the particles which, let's say, are responsible to the propagation of light. A photon has an energy that is proportional to the frequency, and the proportionality constant is this universal constant called h, which is Planck's constant. It is something like 6.64 times 10 to the minus 34 joule times second. Of course, these are universal constants, they are good to know. Photons have no mass, they only have energy, and they have a fixed velocity. They move with the speed of light. Okay, it's useful to consider what is the energy of a photon in the visible light spectrum. So we know how the frequency is related to the wavelength, so we can do the calculation easily. So E is equal to h times c over lambda, because f is equal to c over lambda. So for example, we can make a computation. I can give you the results, of course. For the red end of the spectrum, we have lambda equal to 780 nanometers, and if we make the calculation, the energy of a photon is 2.55 times 10 to the minus 19 joule. So it's a very, let's say, small number in this unit of measure, and that is the reason why we typically use a different unit of measure. Okay? Instead of using joule for discussing the energy of photons, we typically use another unit for energy, which is called electron volt. The symbol is EV. EV stands for electron volt, and is basically the charge of an electron times 1 volt. Okay, a charge times a volt is an energy, and therefore the charge of an electron is 1.6 times 10 to the minus 19 Coulomb times 1 volt is equal to 1.6 times 10 to the minus 19 joule. So of course 1 electron volt is a very small energy, but it is very useful to use as a unit of measure for photon energy. You see the exponent of the power of 10 is exactly the same. So this energy for lambda equal to 780 nanometer is equal to, I do not have the number here, I need to make the calculation. Let me check. 2.55 over 1.6 is 1.6. Let's see, 1.6 EV. Okay, which is easier to remember. So the other end of the spectrum corresponds to lambda equal to 380 nanometers, and in terms of energy gives us, we need to okay, we can use the proportion, of course, because in order to do a simple calculation we have to take 1.6 to multiply by 780 and to divide by 380, and it is 3.28 eV. So this is what we need to stress. The energy of a photon in the visible spectrum is between 1.6 electron volt and 3.28 electron volts. So why that is important? Because this is the type of energy that we need in order to produce photons. And in order to let's say, produce light, we have to produce photons, of course. Okay, the main way in solid state electronics to produce a no, I need another page. To produce light is by using a LED, a light emitting diode. Okay, I want just to check briefly the principle of operation, because of course LEDs are important for displays. So a light emitting diode, as the word says, is a diode. I just want you to understand the main mechanism of operation. If we want to have current through a diode, we need to apply a positive voltage between the P part and the N part of the diode. And of course, when we apply, if you remember the operation of the diode, when you apply this positive voltage, we allow diffusions of charge carriers between the P and the N regions. So what we have here is that the holes, which are in large quantity in the P region, can diffuse towards the N regions, and the electrons, which are in large quantities in the N region, can diffuse towards the P region, and therefore we have current. Now, why we can transform this current into light? The thing is that it really depends on the properties of the material. If a diode is not done with silicon, but with, let's say, with other semiconductors, with specific other semiconductors, some very nice thing can happen. Let me explain. One way to discuss the operation of a diode is to plot the potential energy for electrons and the potential energy for holes. So if you remember the operation of the diode, when the diode is on, there's a very small barrier for holes and for electrons, and so this is the reason why we can have diffusion. So for example, this is if this is energy, and this is, let's say, x, the longitudinal direction, this is the potential energy for electrons, and there's a small barrier so that electrons can easily diffuse into the N region. And if I plot here the potential energy for holes, in these plots, the potential energy for holes is plotted multiplied by -1, so negated. Then I have, so that I must look at the energies in the opposite direction. I have a small barrier for holes, and therefore the holes can diffuse from the P region to the N region. So this is exactly this plot, but described in terms of energy. So what happens is that in this central part we have many electrons and many holes, and what can happen is a so-called recombination, which means that a free electron can occupy a place in a bond which was not occupied. Okay, so it becomes not free anymore. By doing that, of course, the electron, the free electron disappears, but also a hole disappears, because this bond which was not occupied was actually a hole. So this process is a process that liberates energy, because the free electron has much more energy than an electron bonded in the silicon, or in general the semiconductor crystal. Okay, and so this is recombination. One needs to remember two important things about recombination. One is that with recombination, both the free electron and the hole disappear, so we have less particles. And the other thing is that there is a liberation of energy, because the free electron has much more energy than the electron in a bond. The energy that is liberated is actually this difference, because this is the energy of the free electron, and this is the energy of the highest energy of electrons connected to the silicon or semiconductor ions. Okay, depending on the type of material, this energy liberated can be transformed in two ways. Can become just heat, because we say it is transformed in a phonon, which is a mechanical vibration of the semiconductor, and that is simply heat. Or it can be transformed in a photon, so in a quantum of light, which is emitted. And this really depends on the type of material, and also some engineering that we can do if we have a phonon, the vibration of the crystal, or light, a photon. For example, in silicon, unfortunately, we do not have light, but in other materials, such as, for example, gallium arsenide, we have light. Okay, it really depends on the type of material. So, in the case of silicon, we have, let's say, mechanical vibrations, which are called phonons, and basically are just heat. But for other semiconductor materials, we have light. For example, in the case of gallium arsenide, this Ga is the symbol for gallium, and As is the symbol for arsenic. The material is called gallium arsenide in English, or arsenico di Gallio in Italiano. Gallium arsenide. Gallium arsenide emits light. At what energy? At the energy of this potential energy difference. So, in order to, let's say, give you the proper nomenclature, let me tell you that this potential energy of electrons is called conduction band energy. Actually, it's conduction band edge energy, to be precise. The potential energy for holes is called the valence band energy. I'm mentioning these names because you can actually encounter it in some other situations. Conduction band edge energy. And the difference between the two, which is also the energy of the emitted photons, is called Eg, which is the energy gap. And the energy gap is, as I mentioned before, a property of the material, but can also be engineered. Okay, basically we can engineer materials, so it's not something that we have to take from nature as it is. Okay, the gap in the case of gallium arsenide is 1.43 eV, which is infrared, essentially, just below the energy of the red. But for example, there are other semiconductors which have a higher energy. Gallium phosphide. This P stays for phosphorus. This is called gallium phosphide, fosfuro di gallio. Has an energy gap which is 2.26 eV, so it's visible and it's green. It's the green lead, essentially. The green lead is gallium phosphide. Actually, it's the most common one, I would say. And then there is gallium nitride. This N stays for nitrogen, which is azoto in Italian. And it's probably the most important material for let's say LED application now, which has an even larger energy gap. It's 3.4 eV, so it's blue. It's a little bit above the blue. Gallium nitride is used for the blue LED, for the blue laser. The blue laser is the laser for DVD and other optical high-density storage mechanisms. And of course, there are other materials, and one can mix different types of materials in order to adjust the gap and emit light at the energy, which means at the frequency one actually wants. Okay? Okay, this is just the basic operation of the LED. Consider that we can play a lot with materials, and it has been done. Because if you just consider the time span of lasers, of LEDs have been invented in the 60s, okay, the beginning of the 60s, and basically until 10 years ago, their use was very limited, okay. Now, of course, we have, at least if you consider the screen and the LEDs used for lighting at home and in cars, etc., the market is incredibly large. And all these 50 years and more have been required in order to improve the technology, improve the material, bring it down costs, and let's say transform something from a nice, let's say nice device to a huge market. And of course, a lot of science in the middle, because science and engineering, of course, because it was required the capability to change and modify the properties of the materials. This was the most important part. Okay, now, okay, this is a way to obtain photons that emit at a very specific frequency, which means light at a very specific color. Okay, of course, in most cases we need white LEDs, for example, for lighting, at home, in a car, and also for displays. And there are several options to obtain white LEDs. Actually, one is combining three different colors, so having an array of a blue LED plus a green LED plus a red LED. Okay, you know that white is a color which comes from let's say the addition of all frequencies in the visible spectrum. Okay, this is the real white. But the other thing that you probably know is that the eye interprets as a white a combination of blue, green, and red. This is just let's say an effect of how the eye works. But basically, let's say with a proper combination of blue, green, and LED, the eye can see just white. Okay, let's say the human eye. This is not general. Now, of course, and therefore this is an option. This is not very commonly used because it has some problem with aging. And the problem is that you tune the light in order to have a good white, and then after some time, for example, one of the 3 LEDs has a reduced intensity because of aging, and therefore your white turns greenish or bluish or something. I mean, which is not a true white anymore, because for LEDs there is this process of aging, and the intensity of the LED changes with time. Since you have different LEDs, they can age differently. So the other very common option is that of having a near UV LED, so something above the blue, for example by a gallium nitride LED, and then to have a phosphor, an RGB phosphor. A phosphor is a fluorescent material. Phosphor is in Italian is fosforo, but is not the element phosphor, which in English is phosphorus. The phosphor is a fluorescent material. No. It's hard to speak and write at the same time. Fluorescent in English. A fluorescent material is a material which can absorb photons at a certain energy and re-emit photons at a lower energy. So, and therefore you want something like you absorb a high energy photon in the ultraviolet range, and then you can, let's say if you had the red phosphor, you re-emit a photon in the red. Then you can have another layer of green phosphor, which of course emit a photon in the green, emit photons in the green, and then you have another layer of blue phosphor which emit photons in the blue. And therefore you have a white. And of course there's no problem of aging with the phosphor. It's the LED which has problem with aging. So this works because even if the LED has an aging problem, you observe a diminished intensity of the white, but you do not observe a change of color. Okay? So, of course, one has to, let's say, design very carefully the phosphor in order to have the proper, let's say, combination of red, green, and blue in order to have a good white. Okay, this is, let's say, the typical situation. The other situation, which is also common, is to have a blue LED, a blue LED. Sometimes, very often, LED is just called LED, and that's it, plus a yellow phosphor. And blue plus yellow, let's say, is seen by the eye as a white in the proper, let's say, combinations. So this is easier than the RGB phosphor. Is a cheaper version. You have a blue LED and then you have yellow, and of course not all photons are absorbed, so you also have a blue here. So, and this is seen as a white. It's not as a good white as the one with red, green, and blue, but it's doable and it's found. Okay. So we have white LEDs. As I mentioned, white LEDs are also used for displays. like this is done with white LEDs, for example, even if it's a color display, but the colors come from another, let's say, type of filtering, from a different type of filtering that we'll see in a minute. Okay, now just continuing our discussion of LEDs, is important to mention the organic LEDs, the OLED. Because they are very, let's say, interesting for displays. So the principle of operation is the same of the semiconductor LED, the one that I have shown you before. The main difference is that the material is not a semiconductor, not a crystalline semiconductor, but is essentially an organic semiconductor, which is used because it can be fabricated by a process which is very close to printing on a large scale. So if I want to make a display with an OLED, let's say if I want to make a display with LED, I cannot use a semiconductor LED because this would be too large. Okay, a silicon chip can be at most 1-2 centimeters squared, 3 if it's extremely large, but it's not good for a smartphone screen, or not even for a TV, for example. But with OLED I can, let's say, fabricate large areas, because essentially what we have is that we have different layers of material which are deposited with a process that is very close to printing at low temperature, and there is a couple of organic layers. There is one organic layer that is N-type. In the lab you can just, let's say, put the layer with pennello, mi manca la parola, l'ho persa. Un pennello si spalma. Brush, with a brush. So an organic layer which is N-type is also called electron transport layer, because it's the layer in which the carriers are electrons, so it's N-type. Electron transport layer. And there's another organic layer which is P-type, different material typically, and it's also called hole transport layer. So as I mentioned, the principle of operation is exactly the same as for LEDs. This junction has to be put in the on state, so there is a bottom electrode and of course here you need another electrode for the other contact, and which is typically a transparent electrode, because you need to emit light from the surface in that case. So let me just this is the transparent electrode. And then you have glass on top. So when you apply voltage between the electrode and the transparent electrode, you start to emit light, which is emitted through the glass in that direction. So that is the let's say, relatively easy principle of operation of the OLED. The transparent electrode is a critical piece of the component, because of course you cannot use a metal as an electrode because the metal is not transparent. Good transparent electrodes are actually some oxides, some conductive oxides, and the most commonly used is called ITO, which is indium tin oxide, and it's probably the most common one. ETO, which is indium tin oxide. It is an oxide, so it is not a wonderful conductor, but it's a relatively good conductor, and it's very transparent, so it can be used for these applications. Okay. Actually, we tried a couple of years ago to use graphene as a transparent electrode in the case of LEDs and of solar cells, because graphene is a good conductor and it's also transparent. It's actually, at the moment, is less reliable than indium tin oxide, but I mean, it's a good candidate for substituting indium tin oxide, because it's more conductive and more transparent, but at the moment is less reliable for this type of applications. Okay, that's it. There are many different types of organic layers that can be used. There are small molecules or polymers, and that's a huge industry for LEDs. It's a large industry. It's not a niche market. They are used in many different applications. For the moment, mostly for small screens, because they are expensive for large screens, but the market is really increasing. Okay, so this is a single LED. How do we build a display? In order to have a display, of course, one needs to have essentially an array of LED, and one has to drive them. So what are the options? Basically, there are two options. One is the one of having passive matrix displays. In the case of a passive matrix display, one has an array of LED. Oh, by the way, the symbol of an LED is similar to the symbol of a diode plus flash. Okay, so this is the symbol of one LED. Just for the purpose of explaining how a display works, I'm just putting 3 LEDs by 3, so 9 in total, a 3 by 3 array. Let's assume that this is the array. Okay, and in order to drive this array, we use the perimeter of the array. So basically, we need to have one transistor for each column. Okay, I'm using a bipolar transistor, but an FET could be used as well. Okay, and we drive with the columns all the P parts of the LEDs. So this goes to VDD. And this is, let's say, C1, this is C2, this is C3, 3 different signals. And then we have some, we drive the N regions by row. So we have a row transistor, driven by R1. Let's say another row transistor driven by R2, and another row transistor driven by R3. Okay, of course you can generalize to a much larger matrix. Then what we can do here is to turn the light on column by column, and actually we do it in the following way. Basically, let's just to, let's say, have an example that is complete, it can be understood. Let's consider the driving of this array. So we have 6 signals, and I'm drawing 6 lines. And then, and for example, you see that the column transistors are on if the control voltage is low, because they are PNP. So for example, if we want to turn on C1, we need to add a negative voltage to C1 like this. And then let's assume, for example, that we want to draw this image. We have a 3x3 display, and then we want to draw an image which is like this. Okay, this is just an example, but okay, so we need to turn the light on this one and this one, and in order to turn the light on, we need to put a high voltage on R1, because if we put a high voltage on R1, then this transistor goes on, and we have current through the diode. So we need to put a high R1 and R3. So this is C2, C3, R1, R2, and R3. At this instant, we need to put R1 high and R3 high, and this is low. Okay, then we switch C1 off, and then we can switch C2 on, and we need to we need to turn on R2 and R3. So it is like this, and then R2 and R3. This is the second, and then it's in the third column we need to turn on only this last one. So we put C3 low, and then R3 high, and that's it. And then we start again. So we have to scan column by column. Of course, the image is composed by the eye, okay, because basically it's like a scan of the image. Of course, the LED is switched off, but basically the eye does a low-pass filtering, the eye plus brain, okay, does a low-pass filtering and constructs the image, like with the laser scan displays, basically. And of course, this image has to be refreshed continuously in order to remain. So after this part, we need to scan the first column again, and so on. Okay, this has to continue then. This is relatively easy from the point of view of let's say, driving the LEDs. Of course, if you want to drive to have color display, you need basically at least one LED for the green, one for the red, and one for the blue per each pixel. But of course, it can work. It's not very common now. It's mainly used only for very large areas, but very large, for the maxi displays. So I have a figure here. Oh, this is large enough. Okay, this is a Passivematrix display, because otherwise you cannot do that. Okay, it's really huge. This is doable if you have a large LEDs. You can have large pixels, and of course it can work. Apart from the most common situation instead is the active matrix display. So in the case of active matrix display, we have an array again, which is organized as an array for memory. We have, for example, word lines and bit lines, and of course, in order to turn on an LED, you need to have a high voltage on the word line and then a high voltage on the bit line. And then at each crossing you have a transistor plus a capacitor, and in parallel, like a DRAM. Now this is the situation of a DRAM, but in parallel to the capacitor you have the LED. This is the easiest situation. So when the word line is high and the bit line is high, the transistor is turned on and the capacitor is charged at the voltage of the bit line. Okay, and then of course also the diode is at the voltage of the bit line. And the reason why you have a capacitor is that when you go to the other pixel and then you turn the transistor off, the capacitor keeps the voltage on the LED, so that the LED can continue to emit. Okay, that's the basic circuit. Okay, the capacitor is only needed in order to continue to supply voltage on the LED. Of course, when the LED works, the voltage on the capacitor goes down because you have current through the LED, but you have to dimension everything in order that the LED can stay on until the screen is refreshed again. That is the main thing. Of course, it's not wonderful because you see that the light emitted by the LED decreases in time, so it's not constant, but this is the very basic circuit. By adding a couple, at least 3 transistors per pixel, you can do it in a way, you can adjust things in a way that the voltage remains constant until it drops instantly. So at least you have a uniform, let's say, intensity as a function of time. But okay, this is just to, let's say, understand the basic operation. So for each pixel you need 1 transistor plus 1 capacitor plus 1 LED. Okay, 1 transistor plus 1 capacitor per pixel. Now you need to understand that this is a display, so it's a large thing. The transistor cannot be a semiconductor transistor, a normal silicon transistor, because you cannot build an integrated circuit as large as a display. Okay, and these indeed are different transistors. They are so-called thin film transistors. Which are also called TFTs, thin film transistors, and are also in that case obtained with a process that is similar to printing. It's very cheap, it can be done on large areas. So basically you have a layer for the gate, for example. Basically, it's very, very similar to printing in this case, because you're printing on large areas. So then you have an insulating layer, then you deposit on top. Then you have a semiconducting layer that you deposit on top of it. Okay, so this is the insulating. This is the semiconducting layer. and then in order to have a transistor you put some metal layer, some conducting layer to have the source and drain electrode. So this is the source, for example, and this is the drain. You have the same layer for the two contacts, drain. So all these transistors are done in a very simple way. The gate is always on the bottom, and they're not very small. I mean, the point is that you don't need high performance transistors, because the clock frequency is going to be just a few megahertz. So you really don't need a high performance transistors. You need something that is cheap and that can be fabricated on large areas. And in this case, these P-film transistors can be organic or not organic materials. It really depends on there are many different options. And with a very similar technology, one can obtain both the thin film transistors and the LEDs. Okay, so different options are, let's say, a polycrystalline silicon. This is the best performing and most expensive. Or organic semiconductors. Or also amorphous silicon works, but okay, it's I don't want to mention it explicitly because it opens another another issue. Okay, the typical common screen that uses this type of solution is the so-called AMOLED. You probably have heard it because it's a commercial name. The AMOLED, for example, is used on the Galaxy S series by Samsung. And also, for example, the iPhone 8 started using the AMOLED. So until 7 it was LCD screen, and from the 8 it's AMOLED. And AMOLED means active matrix OLED. So the architecture is the active matrix architecture. So it's a DRAM-like architecture, and the LEDs are organic LEDs. Okay. They are very, very nice. Now for smart screens are for smartphones are quite common. For TVs are very expensive yet. So I mean, you can see some AMOLED TVs, but they are in the expensive range. The thing is that the technology is not expensive. The yield is complicated because it's very hard to have good colors with AMOLED. It's very hard. It's very nice as a technology from the point of view of energy consumption, because the screen has a very low energy consumption, but the color quality is hard to reach, and also the aging is a bit of a problem. So this is why the solutions is expensive. This is why, for example, Apple used it only at this generation, because it was not happy with the quality before. Okay, but it is a technology which is going to become more and more common. Okay, so it's important for me to give you an idea of the let's say complexity of the display, because of course you can think, if you have an HD screen, full HD screen, you have 1920 columns and 1080 rows, so about 2 million pixels Okay, and then of course it's a color screen, which means you need green, red, and blue. So typically the situation is like this. This is an image of let's say structure of the pixel, which is called diamond pixel, that is very commonly used in the case of AMOLED. And you see you have a different density of greens, reds, and blue. Typically you have a number of green LEDs which is equal to the number of pixels. So you have basically 2 million green LEDs. And then you have 1 million, half the red and half the blue. So 1 million blue and 1 million red LEDs. And this is, and the reason for that is because you know that the eye has a lower definition on the colors, so you need a high definition for the intensity. But even if for the colors you have a smaller definition, it works. The eye does not notice, basically. Okay, for each of these 4 million LEDs, of course, you need a specific addressing circuit and TFT plus capacitor, plus in practice you have a few more transistors to keep the voltage on the LED constant until refresh. So you have a few few tens of millions of transistors for a typical full HD display, all with TFT technology. Okay. Actually, at the moment, the most let me use a new the most used technology for LCDs, for displays, is the one based on LCDs. LCDs stands for liquid crystal displays. And for the moment is much more common than an LED display. So let me just tell you what is the principle of operation. So the liquid crystal display works on polarized light. So we need to start from polarized light. Let's assume that this is vertically polarized. Typically, vertically polarized light is obtained by normal light, unpolarized light that passes through a polarizer. Okay, so let me just check what is a polarization. What is light polarization? Okay, just let me just briefly mention it in at least a couple of things. If you think of light, light of course is an electromagnetic wave. If light propagates in this direction, okay, this is the velocity of light, along with light you have an electric field and a magnetic field propagating. So that's why we say electromagnetic field. And the electric field oscillates along a direction, typically, and the magnetic field oscillates along an orthogonal direction. So the polarization of the light is the direction of the electric field. In a vertically polarized light, I have a vertical electric field which is oriented in electric field which is oriented in the vertical direction and propagates along this line. This is the field at different positions along the wave. And then there is a magnetic field which propagates in this other direction vertically the magnetic field is called with H, okay, and light and the wave propagates in this direction. So you have an electric field and magnetic field which oscillate at the frequency of light, or at the frequency of the photon, propagating with the speed of light along one direction. So this is a vertical polarization. You can have a horizontal polarization, and in the case of an horizontal polarization, the electric field oscillates in the horizontal plane, okay, like this. So this is the intensity of the field at various stages, and of course you have the magnetic field, which is instant by instant orthogonal to the electric field, and this is an horizontal polarization. So normal light coming from the sun or from a lamp is typically not polarized, which means that you have, let's say, half in vertical polarization and half in horizontal polarization, half intensity and half intensity. So you don't, there's no reason it to be polarized. The polarization is completely random, which means that you have half and half. But then, of course, because of reflection, it can become polarized. For example, typically light that is reflected on the water, on the sea, is reflected with an exclusive horizontal polarization. And this is why when you're on the beach you use the polarized glasses. That's the main reason you use that. Also, sky becomes polarized because of reflection in the atmosphere. But apart from that, typically light is not polarized. If you want to polarize it, you use a filter that eliminates the horizontal polarization and lets pass through only the vertically polarized light. Okay, that's for start. Okay, now the liquid crystals come into play. Basically, you need to have you have an electrode, which needs to be a transparent electrode, of course, because light has to pass through. And then in the middle, you have this chamber with liquid crystals. Liquid crystals are immersed in a solution. They typically are in a random orientation, which is more or less horizontal in the solution. And when they are in this orientation, they do not change the polarization of no, when they are in this position, no, sorry, when they are in this position, let me just, I don't want to get confused. Yes. Yeah. What happens is that when let me finish the drawing. This is the electrode. And this is the solution with liquid crystals. And then you have light passing through. Now we see what happens if we apply, what happens to the polarization. Let me conclude. If instead you apply a voltage, this is what happens if you apply zero voltage between these two electrons, zero voltage. If you apply a voltage between the two electrons, these liquid crystals align in, let's say this is the situation, align in this vertical direction. Okay, you change the orientation of the crystal, and something happens to the light, vertically polarized light. So in this situation, the polarization does not change. So here you have vertically polarized light. In this situation, the polarization starts to rotate during transport in the solution. And basically the thing is to design the length of the solution so that after this space the polarization is horizontal. So the polarization has rotated by 90 degrees. So in this situation you have here horizontally polarized light. Okay, then if you have different polarization, now you can select. You apply here an horizontal filter, horizontal polarization filter, which means that in this case you have light horizontally polarized light, and in this case the light is completely blocked because the polarization is wrong. So by turning on and off the voltage applied to the liquid crystals, you can let the light pass through or not. Okay, that is how it works. So there's a huge difference with respect to the LED case. You need to have light from the back to polarize it vertically, and then you can just, let's say, allow transmission of light or do not allow transmission of light. And this is basically how the LEDs works. And there are two consequences. One is that it is extremely easy to make single color LEDs screen because it is easier, of course. And the other thing is that typically the light that is emitted from an LCD display is polarized. In this particular case, is horizontally polarized, and this is the reason why, for example, if you wear polarized glasses, typically you have problems in looking at LCD displays. In my case, for example, if I look, I cannot see I have an LCD watch. I cannot see the watch with polarized glasses. And this, or in the car, typically happens. It is quite common. So, how this principle is used in practice? Let me just show you this part. This is a color LCD screen, for example, like the one that most of us has in our computers. You see what is the situation? You need to have light from the back, which is generated, for example, by LEDs. You need to have light. Then you have a polarizer. Then you have, this is the polarizer, because you need to start with polarized light. Then you need to have the liquid crystal fluid, okay, and the back panel, which is the back electrode, and the front electrode, which I described before, and then the polarizer in the opposite direction, so that you can do the selection. In the middle, you need to have a TFT matrix, because you need a transistor to control each liquid crystal pixel. Okay, so for each liquid crystal pixel you need to apply the voltage, or not to apply the voltage, so you need a specific control transistor, and the matrix similar to the active matrix display that we have seen before. So from the point of view of architecture, it's similar to the active matrix architecture, but instead of an LED you have an LCD, which does not emit light but only acts as a filter. And then in order to have colors, you need to have some filters, typically fluorescent filters that transform the blue or white LED light from the back into a blue, a green, or a red. Okay, and this is the typical situation. Actually, it's at the moment, as I said, is more common than the LED solution. One typically in this case, commercially sometimes they are called LCD backlight LED, because the backlight is done with LEDs. But actually, you have just let's say some LEDs in order to provide the backlight, but the actual pixels are only filters. Okay. I mentioned before that the AMOLED is more efficient from the point of view of energy, and you probably can see the reason. In this case, if you have a black, for example, with the AMOLED, in order to have a black, you have all the pixels off. All the LEDs are off. In this case, in order to have, when you have a black with the LCD screen, when you have a black, actually you have the backlight that is white, and you have all the LCD off so that you don't see the light. But you basically are, let's say, consuming power. Okay, that is the main difference. The power consumption is constant for the LCD screen, but it can vary depending on the color for the AMOLED.